What if we could harness the laws of the quantum world, the strange realm where particles exist in multiple states at once, to create machines that operate with unimaginable efficiency? What if the future of energy, computing, and sustainability depends not just on how we use power, but on how quantum systems use energy at the smallest scales? Welcome to the Learning Studio, and in today's episode from our physics playlist, we'll explore one of the most exciting frontiers in modern physics, quantum thermodynamics. You can watch the complete physics playlist by clicking the link below in the description. This topic belongs to our section Quantum and Relativistic Revolution, where physics meets computation, where we uncover how the principles of the quantum world are reshaping the future of technology, computation, and energy itself. From classical heat to quantum energy. For over 150 years, thermodynamics has been the science of heat, energy, and work, the reason why engines run, refrigerators cool, and stars shine. It's guided by timeless principles like energy cannot be created or destroyed, only transformed. Entropy, the measure of disorder, always increases over time. But when we zoom into the quantum scale, something extraordinary happens. The smooth, continuous flow of energy breaks down into discrete packets, quanta. At this level, heat, work, and entropy become fuzzy, probabilistic, and even reversible under certain conditions. That's where quantum thermodynamics begins, the study of how the rules of energy transform when quantum mechanics enters the picture. The quantum engine, energy at the smallest scales. Imagine a heat engine so small it's made of just a few atoms. Now imagine it can exist in multiple energy states at once, generating work using quantum superposition and entanglement instead of pistons and fuel. That's not science fiction, it's happening right now in laboratories around the world. Physicists are building quantum heat engines, tiny machines that operate using the same quantum laws that govern atoms and photons. Unlike classical engines, these quantum systems can extract energy from coherence, the same property that allows qubits in a quantum computer to process multiple states simultaneously. This means quantum engines can, in theory, achieve higher efficiencies and lower energy losses than any classical device. And the same principles that make them possible also apply to quantum computers. Quantum thermodynamics and computing efficiency. Quantum computers are not only about faster calculations, they're about smarter energy use. In classical computing, every operation consumes energy and produces heat. But in quantum computing, information is stored in reversible quantum states, meaning energy can, in principle, be conserved more effectively. Quantum thermodynamics provides the theoretical framework for designing energy-efficient quantum processors, cooling systems, and even quantum batteries, devices that store and release energy using entangled particles. These aren't just futuristic concepts, they're being developed right now to support sustainable computation, computers that think faster, run cooler, and consume less power. Machine learning models are also being used to simulate quantum thermodynamic systems, allowing AI to predict how quantum devices will behave under different energy conditions. It's a collaboration between physics, AI, and engineering that could redefine how we think about both computation and conservation. Entropy, information, and the arrow of time. One of the most fascinating aspects of thermodynamics, both classical and quantum, is entropy, the tendency of systems to move toward disorder. It's what defines the arrow of time, why we remember the past but not the future. But in quantum systems, time doesn't behave so simply. Quantum information can, under certain conditions, be reversed. Entanglement allows energy and information to flow in ways that challenge our everyday understanding of cause and effect. This has deep implications not just for physics, but for AI, data science, and computation, where entropy is directly linked to information loss and efficiency. By studying quantum entropy, scientists are learning how to design algorithms, and even computers, that mimic the universe's most efficient systems. Towards sustainable quantum technology. At its heart, quantum thermodynamics is about harmony between energy, information, and efficiency. It bridges the gap between fundamental physics and practical technology, guiding us toward machines that respect the limits of nature while expanding what's possible within them. In the coming years, this field will be vital in designing quantum data centers with minimal energy waste, creating quantum batteries that charge in seconds, developing AI-optimized quantum engines for clean energy systems, and helping humanity balance progress with sustainability, not by fighting physics, but by understanding it more deeply. This is the Learning Studio, and this was our episode on quantum thermodynamics. If you enjoyed exploring how quantum physics could revolutionize both energy and computation, make sure to subscribe, like, and check out the physics playlist linked below. In our next episode, we'll explore the most ambitious idea in all of science, quantum gravity and the unification quest, where we attempt to merge Einstein's curved spacetime with the quantum fabric of reality itself. Because in physics, every bit of information, and every quantum of energy, matters.